What did I say?
He's coming back. Okay, so let's move on swiftly to the last talk of the morning session by Adam Johansen, who's going to talk to us about divide and conquer sequential Monte Carlo. Adam.
Thank you, Dan, and thank you to the organisers of this workshop, which I'm very much enjoying, both for organising it and for giving me this opportunity to speak. So I'm talking, as Dan said, about something we call divide and conquer sequential Monte Carlo, which is something I've been thinking about on and off for about the last 15 years. One consequence of which is the number of people I've been thinking about it with has grown rather long. So I've listed the main culprits on this slide. I won't go through the list in detail, but some of them are in this room and some of them were earlier this week. Simplicity has come up a lot this morning, and monotonicity is something I like, so I'm going to maintain the non-decreasing simplicity that we've had this morning. In fact, if you reach the end of this and reach the conclusion that the algorithm is fairly obvious and there's nothing very surprising about the theory, then I've probably done a reasonably good job. If you also think it might conceivably be interesting in at least some situation, then that's a bonus from my point of view. But I'm going to begin by saying a little bit about sequential Monte Carlo, which is a bit pointless in this meeting because everyone knows a lot about sequential Monte Carlo, but it will allow me to phrase things in a particular way, which then makes what follows hopefully seem fairly natural. If you don't rewrite the basic things in the right way, then what follows may seem a little more esoteric than it really is. I'm then going to talk about divide and conquer sequential Monte Carlo, which isn't obviously a sequential Monte Carlo algorithm per se. It looks very much like one. It has a lot of the same ingredients. It's inspired by one, but it's not sequential, at least in the way you would normally write it. I will at some point demonstrate that you can write it sequentially as a kind of evolving structured population model, but I don't think that view is particularly useful from the point of view of implementation or analysis, but it might help to think about it in that way somehow. I'll talk a little bit about the theoretical behavior of this class of algorithms before sketching a couple of recent illustrative applications of the method. I don't think either of these are necessarily the ultimate solution to any particular problem. They seem to work okay for some stuff. I think that there's more to do in these directions. Move on. So sequential Monte Carlo, we have a sequence of distributions defined on an increasing sequence of state space. It's important they're increasing. The way that things are normally set up, that doesn't necessarily mean we have to care about all their coordinates. It doesn't mean we believe we can approximate them all necessarily. At least formally, this is what we're doing, and we have some normalizing constants that are called Z of some unnormalized target measures rho. We have normalized counterparts which I'm calling mu. This is going to upset Pierre, but it's notation in the paper, and we needed lots of measures, so it all got messy. So yeah, the notation's slightly different there, but it doesn't change anything. We have some proposals which are essentially conditional laws over the next point in this path space, given what came before, and we have some potential, some important points which are a change of measure from one distribution in that sequence in the proposal to the next distribution. So we want to do things like approximate the sequence of normalizing constant, or maybe just the final normalizing constant, and approximate the sequence of normalized measures, or maybe just the final. So this is all good, and you can write out a long fiddly algorithm, which I wouldn't normally do, but it's kind of handy to have things written in exactly the same form that things will come later, so you can see that not very much has actually changed moving from this to subsequent algorithms. So you do some important sampling to initialize it, and then at each iteration you do, the way I've written it here, you do some selection based on the empirical measure. I said we should do this independently. That's what we did in the analysis, because we wanted to show how it related to standard SMC rather than absolutely minimize the assumptions or work under the most general possible conditions. And I think essentially everything that can be done to generalize the kind of result I present in the standard SMC will apply here, mutatis mutandis, as it were, but it was messy enough already. So we'll stick to assuming we do things multiple. Obviously, don't in practice. And then there's some mutation, which I will view as drawing an extra variable from the conditional law and concatenating it with what you've got, correct to obtain this unnormalized measure. So the normalizing constant there maintains this sort of path space. unnormalized measure property and carry on. So we all know this. We've seen lots of algorithms that look like this week, and you can do filtering with it. Another thing you can do with it is the sequential Monte Carlo sampler kind of thing, which Arno touched on a few days ago. And I mentioned this because this construction shows you how you can work on sequences of state spaces which don't have that kind of strict increasing property of interest by constructing an artificial sequence which does. And exactly the same thing applies in the divide and conquer setting. It's just the way it's normally written. We don't bother saying that because it can be embedded in exactly the same framework with no additional effort. But it will ultimately be important, and the theoretical results demonstrate why you will need to do this kind of thing, just as you do in the standard setting eventually. So for these algorithms, there's a lot of theory. Establishing it has taken quite a number of people, quite a lot of work. Yeah, in particular, gets mentioned on this slide for obvious reasons, but there are lots of things we know about these algorithms. We can obtain unbiased estimates of the normalizing constant, which at least some people have known since 1996, even if I've been lazy and cited the book. There are strong laws of large numbers, there are central limit theorems, there are asymptotic variance expressions, which although horrendous when you first see them, are actually quite informative about what's going on. So if we're going to arrive at similar algorithms, we'd like to be able to demonstrate that they have similar properties. Something which is common in the engineering literature, but perhaps not so much in a lot of other places, is the auxiliary particle filter of Pitt and Shepherd. I like to think of this as being another particle filter for a different sequence of distributions, and then an extra change of measure at the end to correct for the fact you didn't use the sequence of distributions you actually care about. So you can view it as introducing another sequence of target distributions, some auxiliary target distributions, which have their own normalizing constants, their own normalized analog. And the importance weights here are for the auxiliary target. So I introduced this gamma t minus here, which is essentially what you get in the auxiliary particle filter by reweighting particles before resampling to take into account in the filtering setting the next observation as things were first introduced. So it was introduced as a kind of extra auxiliary reweighting step, but you can think about it as just defining a new sequence of target distributions and then running an algorithm to target those. And then in order to extract estimates for the sequence you originally had, you need to correct for that by an additional. This is all established at this stage. And so there's another algorithm, but it's the same algorithm as before, it just now the target distributions have changed. So nothing has changed here. And I say this only because this is quite a useful way to think about one of the weighting steps in the divide and conquer sequential Monte Carlo algorithm that's going to emerge in a minute. And I think other attempts at explaining it have confused people more than the idea really justifies. So, and you can extract from this algorithm estimates for the measures you actually care about and the normalizing constant you actually care about by a very simple extra weighting step. If it helps anyone, you can sort of obtain Pitt and Shepherd's auxiliary particle filter by setting these auxiliary targets to the product of the original target and an approximation of the one step ahead conditional likelihood. Then everything drops. So that's a very quick introduction to SMC for people who already know a lot about SMC. So I can now move on to this divide and conquer sequential Monte Carlo algorithm. See if I can make this clear. So lots of models admit natural decompositions into smaller models. And there may be all kinds of reasons that it's desirable to do inference, first of all, for small models, and then somehow combine those inferences until you get to a good inference for the original model. It may be that this is a computational device to allow for parallelization or distributed computing. It may be that each of these models corresponds to a kind of local model for a particular subset of the data that can't be shared, and what you actually want to do is inference for a Bayesian hierarchical model like this one. And in order to do this, one strategy is one you might think of as divide and conquer. You turn the original inference problem into one where you divide by splitting the model into submodels and then applying the same procedure to it. You get to the end, you combine those inferences going back in the other direction. So in order to do this, we need a tree-like structure because we need to have a way of recursively dividing the model into smaller parts. And At this point, I think the original presentation convinced people this was primarily useful if your model looked like a tree. It might look like a tree. It doesn't really need to look like a tree. What you need is a tree-like decomposition of models. And so one of the original examples was a lattice model, and there's no particular difficulty with that. And people have worked on state space models using this kind of thing, as I'll say in a bit. So going back to the Bayesian hierarchical model on the previous slide, in order to use this method, we need to have a tree of models. Here, there's this rootward variable inclusion thing, meaning every model contains at least all of the variables that its children contain and possibly some additional ones. So the simplest case you could think about would be a line graph where time goes in this direction, you have none of the other edges in this graph, and every time you add an extra time point on, you have an extra state and an extra observation. The standard state space model fits as a kind of trivial line graph into that setting, but that's then not how you would decompose it if you wanted to do divide and conquer things. And so you have a tree of models. Those models may or may not themselves look like trees. The root of this tree of models is your original model, and as you go down, you get simpler and simpler models with fewer and fewer variables. It's useful to have some notation for the children of any node. In practice, if you're doing this, it's likely that you're going to have a binary tree because the cost of implementing this, at least naively, is going to be exponential in the maximum degree of the tree. So probably that's going to be 2. But it's nice to have general statements. ET is the variables attached to a node which are not included in its children. So in this example, it would be X4 for this node, given you've got these other variables down here. It then includes both of those and an additional thing. And bold E is all of the variables, so both the one attached to this node and the ones which come from its children. And of course, in principle, you could combine this with kind of the SMC sampler construction to arrive at situations where you can refresh the variables that come from lower down the tree. That's unnecessary for big enough models, but it doesn't change anything. So, and divide and conquer SMC is a recursion over this tree. In fact, it's divide and conquer in the sense of being a design pattern, divide and conquer algorithm, unlike most of what people call divide and conquer in Monte Carlo. So it is recursively calling the same algorithm on subproblems. So we've written it in that form, which makes it look perhaps a little bit more arcane than it needs to, but it's quite a useful way to think about it. So if you call this divide and conquer SMC algorithm, you begin by calling it on the root of the tree. So in your original model, that's not a root. So the first thing it does is call the same algorithm on all of its children. And so you recur straight down to the leaves of the tree, and actually you do all your computation from the bottom up. The algorithm looks like it works the other way. And so when you get to a leaf, you do some importance sampling. Actually, the way we have things set up, the auxiliary targets associated with the leaf at that point are just the proposal distribution, so there's no weighting to do. When you move one step up, you then take, for each node, you're calling it on all of the, you've just called it on all of the children and got the response. So you've got a particle approximation for all of the children of this node, which you then multiply together to get a product of empirical measures. So this is where the cost is going to scale horribly with the degree of the tree. And so binary trees are your friend unless you're doing something quite clever to reduce the cost. There are things you can do. You then correct. Well, what you'd like to do is come up with the best approximation to the marginal over the variables that you've got from those children of the target at this level in the tree. So this is exactly what's happening in an auxiliary particle filter. It's the pre-weighting step before you resample. And so we've got this gamma u minus, which is weighted in order to approximate that. You then resample to get back down to n particles for this node. You mutate in the sense of sampling the new variables you might need. And you now have a particle approximation of the auxiliary measure at that node. You can do a trivial resampling step to extract an estimate of the actual target at that node. And then you just recurse. So the notation's horrible. It looks a bit weird when you first see it, but the only thing that's different to a standard sequential Monte Carlo algorithm is this parallelizable, distributable, recurse and combine step where you split the model into pieces, you call an algorithm on those pieces, you glue the answers together before you do the usual mutation selection type dynamics. So there's really not much else going on. And so in about 2014, I looked at this and thought, well, it's a pretty simple algorithm. We know how to analyze algorithms like this. It doesn't involve doing a great deal of theory, so we should be able to show it has about the same properties, and it should be quite a simple argument given what is known at this point. There's a paper in Annals of Applied Prob a month or so ago, which establishes that hypothesis is true. It is really simple. You don't have to do that much. It took an awfully long time to work that out. So with the help of Wankens and Francesco Cuscinio in particular, we've managed to establish that these algorithms, under assumptions which are stronger than necessary, but not that unusual in this community, behave reasonably nicely and very similarly to SMC. So these assumptions are not crazy. The first is that all of your importance weights are well-defined and everywhere positive. I mean, you can relax this, I'm sure, but it made life a little bit simpler and the maths was tedious enough as it were. And the other is that all of the importance weights are bounded above. Again, probably not essential, but it's not harder than it needs to be. And under these assumptions, you can obtain various results which are not very surprising. So you get LP errors, which under those assumptions converge at a root n rate for any bounded function. So if you look at the error between the approximation at any node in this tree of the unnormalized actual target and the approximation of the unnormalized target and the actual target, or the normalized analog, it converges at a root n rate. And indeed, so there's the normalized. So this is not particularly surprising, not particularly exciting. And the only thing it's really going to require beyond taking care of all these indices and the standard argument is some mechanism for controlling the LP error when you take two convergent empirical measures and multiply them together and try and do stuff. So that's the only point at which there's any difference. And, you know, sorry. And of course, you can use the standard kind of Markov or Cantelli kind of argument to involve a short convergence, should you wish to. And if the spaces are Polish, you can then use the standard countable determining class kind of machinery to say that the empirical measures are going to converge weakly. So I think it's quite useful to think of this as being a method for approximating the measures themselves rather than integrals per se, because doing things recursively, you want to know the approximation of the distribution in a fairly general sense. So although referees keep telling me you shouldn't look at almost short convergence of particle filters because they don't need to be defined on the same probability space anyway, I'm not sure I'm persuaded. So this follows from the LP convergence in the usual way. So there's basically nothing new there. So this is perhaps the slide at which things get interesting. And again, there's nothing surprising if you've looked at expressions like this before. I apologize to people who haven't, to what's going on, but this is what you would have guessed the answer was, I suspect, if you're asked to write down an asymptotic variant and you were familiar with the standard results. So we have the usual square root of, the square root of n times the sample approximation error converges to some normal with asymptotic variances for either the normalized or unnormalized things which look like this. And what's this? Well, this is a sum over all of the nodes below the node we're looking at in the tree. So in the standard SMC setting, that would be all of the previous time points of the actual normalized target at that node multiplied by a normalizing constant, because you really wanted the unnormalized one, but this makes it look a little bit more like the standard expression, multiplied by a semi-group like object applied to the reweighting you need to get back to the right target at the end of the test function and centered around the obvious object there. So this is for the unnormalized target, so that's centered around the unnormalized integral, and you get an analogous expression with slightly different normalization and a centering arising from the usual delta method kind of argument. So the interesting thing here, and the place where it differs if your graph is not just a straightforward line, is exactly what this semi-group object is. And really it's the analog of the dynamics under the exact model. So in a filtering setting, this is kind of the unnormalized semi-group, which tells you how mass evolves over time. In this case, it's the unnormalized semi-groupoid, if you want to be pedantic, that tells you how you move around the graph. the tree in particular, moving from a descendant of a node up to that node. And its effect is to integrate out everything parallel to that node and then propagate it up the tree according to the exact mutation selection, well, the exact mutation reweighting dynamics that you have. So that's exactly the same thing you have in a standard sequential Monte Carlo algorithm. But here we have the wrinkle that you're integrating out all the stuff parallel to the node we're looking at in the graph. So you're reducing the dimension of the space on which you're doing the, because these look really like important sampling variances and self-normalized important sampling variances. So this is telling you that by dividing the space up in that way and using this product form to first ordering the asymptotics, the higher order stuff goes away and you end up effectively with an asymptotic variance which allowed you to integrate out the stuff that's parallel to what you care about. Now that's the nice side. That's kind of super cool because that's what you were hoping would happen. And okay, it's a leading order asymptotic statement. It's not going to exactly describe finite sample behavior, but it's not too far off. But the other thing is we've got another term for every node in the graph. So just like SMC, if you run this for long enough, you're going to get more and more terms. And the thing which makes them potentially controllable is this semi-group. Now, if in your graph, all you're doing as you move up the tree is adding some new variables and keeping some of the ones you've got, eventually you're going to be in trouble because you're not moving, you're not changing what you've got before. These variance terms are not going to shrink. And that's the point in the theory where you see you really do need to do tempering if you want to do this for really big models. You need to do something to introduce forgetting. So introducing some Markov kernels, some of the normal machinery is going to be essential. I wasn't particularly surprised by this or particularly disappointed because when I first envisaged these algorithms, I'd always assumed there would be tempering there because I'd seen it as a way of working for large models where you would be able to distribute computing and do large amounts of computing on separated nodes and do this kind of thing. In practice, it seems you can get away with quite large models before you need to do anything like that. And indeed, people have done so. And I think that comes down to the other aspect of this, that you are really reducing the size of the space in which the important sampling is happening to quite a small one. You've got effectively quite large samples because you're multiplying together endpoint approximations to get n squared distinct points. The constants are not bad. So you can work with quite large graphs without doing anything more sophisticated. But this does sort of tell you what's going on, and it tells you there's no magic, and it tells you the rate of convergence is root n, which I'm sure comes as a great surprise to everyone. And you get the same kind of statement for the central limit, for the normalizing constant, and you can rewrite it in a familiar form, the difference being, again, that you've just got a sum over all of the nodes in this tree rather than a sum over all the previous points in a line. And the normalizing constant estimates are unbiased, which, because the things you're multiplying together are independent, is probably the least surprising of things, but it's a nice property because it means if you're really masochistic, you could, for example, embed this within a pseudo-marginal algorithm to make it even more monstrous. So this is the only slide I actually have on the theory, I promise. It's a point which I think is worth making because it's about the one place where you have to do anything other than be careful with standard arguments that have been used for SMC. And that's how do you control the error arising from having a product of empirical measures. And you can sort of write it down, it's fairly obvious in the case where you have two children that you want some kind of expression which is symmetric in those children. Asymmetric, that'd be pretty weird. And there's only one obvious way to do that. And that eventually hints at some kind of multinomial type expansion. And if you're familiar with U statistics, this turns out to be very, very much the same thing you would use there if you're working with a degenerate edge case of multivariate U statistics, which nobody ever works with. So this is sort of in the statistics, the U statistics literature, but it would be the very odd case of a U statistic in which you have multiple samples, but you only use one of each of them. So it's exactly the case that you aren't interested in when you're working with U statistics, curiously enough. And so the idea is, if you have an n particle approximation of each of the children of U, and you want to compare it with U, well, if we add and subtract the actual target, well, the targeted measure at each of those children from this, then we're not changing anything. We can write this quantity as a product over all of the children of those differences. We can subtract this off And then we can do a multinomial expansion of that product, taking the difference of these as one of the terms and the exact thing as the other. Then we can turn that into a sum over all the subsets of the children. The term in which you pick none of the children to be this first term corresponds to killing this term, so that goes away, and you're left with the sum over all the non-trivial subsets of the children of an error term corresponding to a difference between the approximation and the truth for everything in the subset, and just the actual target for all of the other children. And then each of the terms in these products is basically going to converge at the usual Monte Carlo rate. So if you're careful, you can unsurprisingly establish that to the leading order, the only things that matter are the single approximations. That's where. So, as I said, there's nothing very surprising. You don't have to do anything very clever. It takes an awfully long time. So there are lots of things you probably need to do to make these things work eventually in practice. I mean, like any algorithm, it's going to fail if you just apply the vanilla version to an arbitrarily difficult problem and hope it works. You're going to end up needing an astronomical sample size or something. So there are ways of doing the resampling which reduce the cost. Adrian and Nicola and Simo, for example, spotted the fact that since you're sampling from a mixture, if you can bound the importance weights, there are kind of order n rejection sampling approaches, which I think date back to the Mark Breyer's and Arnaud Doucet paper on the auxiliary belief propagation in about 2006, and it's been used in smoothing and all kinds of other places. So in favorable settings, you can make that resampling cheaper, at least in terms of rates, and this may help. In some settings, you certainly need to think carefully about how you do the resampling, because there's a kind of vanilla version of the algorithm presented in the original paper, which said, oh, just do resampling on the marginals and multiply it together, and it'll all work formally, which is true, but clearly the variant is going to be terrible. Clear. You're going to want to do tempering or something like it to introduce some kind of forgetting if the model gets big enough. If the mismatch between the children of a node and the node itself gets large enough, you're going to need to do something to bridge between those. Really a surprise. And this amounts to replacing an important sampling step with a sequence of sequential Monte Carlo sampler steps. It changes the variance by replacing the push forward under the dynamics of things of the important sampling error, but the push forward of the sequential Monte Carlo error is going to behave in very much the way you'd expect. And for big problems where you've distributed this over several disconnected computers, having a lot of computation to do to deal with each of those things is not necessarily a disaster. It might be quite an efficient way of doing things in some settings. The other thing which I think is nice is that it lends itself quite naturally to a variety of forms of adaptation, just as standard SMC does. But here, for example, you might be able to exploit the fact that you have n squared particles before you do the resampling at each stage in the adaptation. Because if, for example, you're doing tempering, you could pick a first temperature such that you have an effective sample size of n or 2n for the first threshold, and actually take the whole population up to that point in one go. And if that threshold is above 1, then maybe you don't need to do tempering at that stage. So there are various things you can do to exploit the fact you've done all this computing. And all the standard adaptation in SMC settings, basically, you can use fairly naturally here. So although I've talked about kind of the most vanilla possible implementation, all the usual SMC tricks can be used, and you probably need them for the same reasons. So I'm going to go too quickly through 2 examples because the details are really quite tedious and nobody needs that before lunch. So one thing it seems to make sense to look at is kind of high dimensional filtering. So a natural question is, can we stick this within a more conventional SMC framework over time to deal with high dimensional state space? We all know you can't really do high dimensional filtering if you don't take account of future observations, because the smoothing distribution and the filtering distribution live in different places. You're not going to have enough information for it to really work, but maybe you can push things a bit further than you can without doing it. So here's the idea in one slide, and it's all rather approximate, so bear with me. We've got time going one way, we've got high dimensional state represented by these slices through it. Maybe at each time we can divide up the model we have implicitly over the states at that time in this divide and conquer way. And then maybe we could do some kind of marginal SMC. So let's integrate out the past by Monte Carlo. Let's just sum over all of the parents you might have had rather than assuming you had a particular parent. And so effectively, at any given node at time t, you basically say, well, I'm going to attach an approximation of the likelihood associated with that node or a group of nodes. I'm going to look at dynamics, which are some approximation of the transition given everything I had at the previous time to that node, and I'm going to integrate out the previous step by summing over things. These FTUs and GTUs are approximations in general, because you're not necessarily going to be able to marginalize the dynamics and the likelihood in that way, but that doesn't matter because you're going to combine them iteratively until you get to the root of this tree again, and then you're going to have an approximation of the whole state, which takes into account the actual transition dynamics and the actual likelihood. And so you get some fairly messy kind of situations, but at the leaves, you sample from something, then you end up with a weight, which is the kind of likelihood and or the proxy likelihood and the proxy transition dynamics. And as in the marginal particle filter, generally, if you choose to use the transition dynamics, then this simplifies that evaluation very considerably. And at the intermediate nodes, you get the same kind of behavior, but you're effectively doing important sampling, taking the likelihood you've got associated with all the observations attached to that point in the tree, divided by the product of those contributions to the level to its children. So if you have independent observations by location, for example, then that's going to go away because there's going to be no difference. So these look horrendous, but they're not necessarily that bad. And you get this really messy order n kind of computation arising from the marginalization of the transition dynamics, which, unless you can simplify things, is horrible. And there are some tricks you can use, and we sort of had an order n to the 5/2, which is pretty bad, but nonetheless, at given computational costs, there are settings in which it can outperform other things. And actually, for a lot of these problems, space is as much a problem as time. So maybe making good use of a smaller number of samples is not such a bad strategy. As I said, these are not the ultimate solutions to some of these problems, but it works okay. And it doesn't impose the same level of restrictiveness on the models you consider that most high-dimensional filtering algorithms people have proposed have. So just as a proof of concept, here's one where the transition dynamics are kind of trivial, but the observations are now non-independent t-distributed errors. So this sort of breaks most of the things people have been working on, unless you just make a crude approximation, because you can't factorize things over location in a nice way. So if you do this, then you can get reasonable estimates. In the paper, we have sort of illustrations showing that, so this is computational cost across here, and it is going up fast. And this just compares an adaptive and non-adaptive version of the algorithm and sort of demonstrates that the adaptation's at least doing as well as, if not a bit better than the non-adaptive version. In 8 dimensions, the bootstrap particle filter can give you some estimates, but they're pretty variable, and they also seem to be pretty widely spaced. We sort of demonstrated it was well calibrated with the bootstrap in a 2x2 grid, but above that, it's kind of hard to get very good comparisons. But the computational cost is not particularly pleasant, but the estimates do seem to be reasonably well behaved. There are other examples where you can see a bit better that it's working okay. I've got bored with linear Gaussian models. So something. And finally, something which is kind of different. This is really from Ryan Chan's PhD, and also involved Gareth Roberts and Murray Pollock. And it's another contribution to this sequence of papers that Gareth and Murray have on combining inference from multiple sub-posteriors. So the objective here is to sample from or approximate F if it can be expressed as a product over a collection of FCs. So the typical example of this is kind of combining Bayesian inference from multiple separated sources, for example. And there's this sequence of work saying, well, actually, if you can construct a density which looks like this, so it's a product of the square of the densities you actually care about and some FC squared invariant transition and 1 over this, then this has the right marginal. Don't worry too much about these expressions, but it tells you there's a target which has the right marginal. And so if you had samples from these FC squared, maybe you could do something, but that's not really realistic. So another idea is to construct a proposal distribution, which looks like a product over those Cs and a Gaussian distribution with some parameters, and use this as an important sampling or rejection sampling proposal. And that's the basis of what they call Bayesian fusion, things like this. So there is a kind of important sampling mechanism for combining sub-posteriors, is by sampling from one thing and doing some important weighting. So this suddenly starts to look like you could stick it into this framework. Okay, so that you can do important sampling. The importance weights are well defined, and if you're familiar with Gareth's stuff on exact simulation of diffusions, this does actually turn out to be something you can get unbiased estimates of. The details are not critical thing. And there's a kind of algorithmic description, and it looks a bit like this, and actually this looks a bit like a kind of important sampling step. You take some samples, you sample some new variables, you sample some more stuff, you compute some weights, you get a weighted approximation. We give the clutter on the slide. Need. That's disappointing. So you could envisage different ways of combining these, because the original fusion idea just took all FC posteriors and tried to simulate kind of Brownian bridges with x at one point, and it gets slow fast, exponentially fast. So you could think about either taking pairs and combining them sequentially. You could think about just adding one more shard on at a time. Either of these give you structures which are amenable to sticking into the algorithm I just described, essentially. And so you get this divide and conquer sequential Monte Carlo variant of the thing, where you just iteratively call it on the children of any one of the nodes in that tree. You get some samples, you combine things. It all works out nicely. It is just an instance of what we had. And if you do this, it's another one of those algorithms that works okay, but is massively expensive, at least in serial implementations, because that's what Ryan was doing. Because this wasn't really about parallel implementation, it was about being able to work with data with situations where you only had sample characterizations of the sub-posteriors. And so here's a graph of how badly it was working. So here's a measure of the error it made in the posterior in a simple kind of situation where you can do everything analytically. And so as the number of sub-posteriors increased, this kind of doing everything in one go thing with any sensible number of samples gets bad fast, because you're doing rejection sampling with a smaller and smaller acceptance probability, or important sampling with higher and higher variance weights, depending on how you do it. Whereas if you do either of those other strategies, they're depressingly close together, so you can't say anything very sense. And then if you look at how much they cost, at least in Ryan's implementation, they're also almost indistinguishable. So we weren't able to say anything very exciting about that aspect of the problem. Some things would be more amenable to parallel implementation and things. So the more interesting thing is if you take some real data and some real model and you try and do, say, logistic regression, with apologies to Nicola, but I wasn't responsible for this. You discover that if you look at the error, this approach works really, really very well indeed. And if you look at the cost, it works really, really very badly indeed. And if you look at the graph which shows both of them, which for some reason I don't have here, you establish that if you want to get the answer right, it's beating all the competitors we were able to find to try. And if you want to get an answer cheaply, it's not as good as any of the other methods in the literature. So if you really do need the right answer, we did seem to be able to get much smaller errors than other methods, even if we pushed them to kind of the limits of the hardware capability. So it was surprisingly effective in some ways and surprisingly expensive in others, but it's not completely hopeless as a strategy. So I should probably just wrap up by saying a few things then. So sequential Monte Carlo is mean field approximation of the Feynman-Ketz flow. It's sequential importance resampling. You can fiddle around with the distributions, the kernels, the various components, but it's always basically the same thing. And this algorithm is just the same thing, but with the occasional multiplying together two empirical measures to get a product measure. And this admits kind of distributed and similar implementation in nice ways. Sometimes maybe you can even do better in serial settings by doing this, by exploiting the structural problems and so on. It works theoretically about as well as SMC. You get the same kind of theoretical properties with the same kind of structure. There are questions which remain, like exactly how you should do this for a lot of problems. If you have a model, you can break it up into chunks in an awful lot of different ways. What's the right way for any given model? Feels like an interesting question, not one I know how to answer. And other people have looked at things along these lines recently. I mean, one particularly interesting thing, Adrian, Nicola and Simo looked at actually applying this to parallelize smoothing in a Monte Carlo way. So it's a kind of gave them a natural analog of the kind of stuff that Simo was talking about yesterday, where you do need to do kind of sequential Monte Carlo and you want to parallelize it. And if you know someone really good at GPU programming, then they seem to be able to get spectacularly good results. So maybe it's not completely. I should stop at that point.
Questions or comments?
On the divide and conquer fusion, like the computational cost, do you know if it's a feature of the sequential implementation or a feature of the ways that you use needing rejection and therefore like maybe getting longer and longer as the...
It's a combination of the two. I mean, doing it sequentially means you have more computation to do, but also there is the issue that depending on how you do it, you're basically trying to simulate diffusion processes with particular properties over potentially longer time periods. It depends exactly how you do the implementation. There are various ways of doing it, but you either are trying to get Brownian motion starting further apart to reach the same point, or something like this. So you either, so yeah, it is in part just that things are not very well behaved once you've got large numbers of sub-posteriors. So I'm a bit skeptical about being able to scale it up just by clever implementation, doing other clever things.
Any other questions or comments? Thank you very much.
Okay.
There's an announcement.
No, yes, we have lunch now, and then as you saw in the program, there is nothing scheduled. You can hear us any other day in the week. It's all the build.